Hello, today we're going to be talking about atmospheric circulation. And we started off this unit talking about different ways that energy transferred in the atmosphere. So all that stuff about radiation and convection is all going to come into play here when we start talking about how air is starting to move around within those layers of the atmosphere that we looked at. So one of the things that we're going to have to keep in mind here is the difference between weather and climate. So remember that in general, when we're talking about this, we're talking about it in the troposphere, and the difference between the two things here is that weather is talking about one particular spot at one moment in time and what the conditions are there then. So it could be temperature, air pressure, precipitation that you're looking at. It's your typical day-to-day weather, whereas climate is looking at it over a much, much longer time span. So you have to look at averages. So average temperature, average precipitation, how things normally change with the season, how they normally vary. And that's going to depend on a lot more different factors here. So it's going to become a little bit more complicated. And now what we're going to start to look at with atmospheric circulation is more of these climate patterns. But we're also going to see how those climate patterns impact our weather on a day-to-day basis. So there's a couple more concepts that we want to remember here in order to understand what's going on. First is latitude, and remember that latitude are those horizontal lines coming up from the equator, and they go from 0 to 90 degrees. So 0 degrees at the equator, 90 degrees at the pole, and they're basically going to tell you how far north or how far south you are. So the higher your latitude number, the further from the equator you are, the closer to the poles, and because of that you're going to get much less solar radiation, and you're usually going to experience less precipitation also. Altitude, on the other hand, is talking about how far away you are from sea level, so basically how high up you are. And you're going to notice that every 1,000 feet that you rise in altitude, the temperature is going to drop about 3 degrees Fahrenheit. And in addition, you're usually going to have more precipitation at lower altitudes and less precipitation at the higher altitudes. So that we're basically going to see when we start looking at biomes that our biome pattern going from the equator to the poles is going to be very similar to our biome pattern going from a low altitude to a high altitude. And that's because they're following similar temperature and precipitation patterns. So that's really where I want your focus to be at this point, is we're going to talk about air circulation, but I really want you to be thinking about how is this going to impact the ecosystems, the biomes in particular areas, because all of the things that we're talking about today are going to have an impact on the type of ecosystem that you could find in these locations. So we're going to find out that atmospheric circulation within the troposphere depends on 4 major things. So the first one is the amount of solar radiation. We've talked about that already, how we're going to get more direct solar radiation at the equator than we are at the poles. Then it's also going to be affected by convection currents that are set up because of that solar radiation coming in. That's also going to be impacting air pressure, and we're going to see different patterns with that. And then the Coriolis effect is going to kind of spin everything around too. So we're going to go through these one by one and see how everything has an impact. So if you remember what we've talked about so far, you remember that no matter what time of year it is, the equator is usually getting most of the direct sunlight. It's going to shift a little bit either direction, but in general, you're getting very direct sunlight at the equator and very indirect sunlight at the poles. And because it's more spread out at the poles, you're just not getting the total amount of radiation coming in there that you would at the equator. Well, it turns out that this is going to set up different zones on Earth in terms of climate. And those zones are actually because it's going to be setting up these different air circulation cells that we're going to talk about in a second. But this is why we wind up with our tropical zone in the middle here, and then our temperate zone, and then as going up towards the poles, our polar zone. And it all comes back to this idea of convection. So just to remind you of how this works, when you have something that is conducting heat, and remember that means the molecules are actually touching in some way, so some sort of hot surface, that hot surface is going to warm the air around it. And as air warms out, its molecules spread out, they become less dense, and as they spread out and become less dense, they're going to start to rise, because we know that less dense things rise. as they rise to their highest amount, in this case this is going to be up into the atmosphere, they're going to hit something cooler. In your house this might be the ceiling. In the atmosphere this is going to be that tropopause. And then once they hit that cooler surface, they are going to start to condense back together, and they're going to become more and more dense, and they're going to fall back down. And this is going to create this convection cell. Now, it turns out that there's also a relationship here to the humidity, or the amount of water that's in the air. So it doesn't actually 100% work like this, but I'm going to explain it in a simplified manner because of the amount of chemistry that you probably understand right now in your school career. So you're almost going to think of air as holding moisture, and think of warm air as being able to hold more moisture. And basically what's going to happen is that when this air is warmed by the surface, usually this is something on the ground that has a really low albedo that's absorbed all that heat, and now it's warming the air right above it. Then that warm air is going to be able to absorb a good amount of water, and it's going to take that water up with it as it rises. And as it rises, it's going to start to cool off, and we know that when things cool off, they condense and they become more dense, and in this case that's going to cause a phase change. So we're going to go from having water vapor back to having liquid water, which is why it's going to rain at that point. Because after the water condenses, it will become heavy enough that it can fall back down. And then at that point, you're going to be left with drier air, which is going to continue to cool off until it sinks back down to the ground. And then the whole cycle can start over again. So we're going to see this cycle of warm, dry air rising, dropping its precipitation, cooling off, and sinking back again over and over and over again this unit. And this is really going to tell us how a lot of our weather and climate patterns work. Now, there's another factor that's really important too that goes along with density, and that's air pressure. So remember that when we talk about density, as we go up in altitude, we decrease in density. So we have the most dense air down by us, and then as we get further away from the Earth and less of a pull of gravity, your air density gets less and less, so you have fewer molecules up here in the same area than you did close to the Earth. And what this is going to cause is pressure is going to decrease as you go up too. So we have a very, very high air pressure down here on the ground, and as we go up and increase in altitude, we're going to get to a point where we have a very low air pressure. And this is actually part of the reason why you have trouble breathing as you go higher up too. The air pressure is so much less, and the density of the oxygen is so much less in the air, that it's very difficult to get enough in every breath. Now, this is also going to go along with temperature. Remember that temperature is essentially a measurement of the amount of molecular movement. So if you have more molecules, you're going to have more movement in general. You're going to have more friction heating each other. They're going to be warmer. So this also explains why it gets colder as we go up in elevation, because there are fewer molecules up there to hit each other. It's less likely to happen. You're not going to get that friction as often, so it gets colder. So this really helps us kind of put all the pieces together, what's happening here, and this is also going to come into play with these convection currents. Alright, so we've seen that density is going to change with altitude, and that's going to change the air pressure. And once again, we're going to have the highest air pressure down close to Earth and the lowest air pressure further up into the troposphere. However, it also changes locally, and when we have local changes in air pressure on the Earth, when we're looking north, south, east, west, this is really where most of our weather patterns come from. So these pressure differences that we're talking about actually come from temperature differences in the first place. And the temperature differences are due to three major things. One could be that maybe a surface has a lower albedo, and because of that it's absorbing more heat, and when it's absorbing more heat, it's able to radiate more heat back into the air around it. So that could be one reason you have a warmer area. Another reason could be that you could have something with a lower specific heat. And remember, something like soil with a low specific heat compared to water, it's going to absorb heat easily. It's also going to give off heat or radiate heat easily back into the air. So a low specific heat substance is going to make the temperature fluctuate more. And then another option could be that maybe it's at a more direct angle of solar insolation, so that light coming in is hitting it more directly, it's going to absorb more heat, and then because of that, it's going to radiate more heat to the air around it. So for whatever reason, some surface is heating up, and when it's heating up, it's going to cause a convection current to start above it. And that convection current is going to cause the pressure difference. So basically, I want you to think about it like this. If you have a surface that is heating up, it would be like in this situation here. What that's going to do is that is going to make that air right above the ground heat up and get less dense and rise. And when it does that, it pushes upwards. So this is going to be an area of low pressure because everything's pushing up away from the ground. So nothing's really pressing down on it. The opposite of that is going to be the other side of your convection current. So as that warm air gets up here and it cools off, it's going to become more dense, and it's going to press down. And at that point, that pressing down, that's that high pressure, pushing down. So think of the molecules as actually pushing down as they sink. And then it would be warmed by the ground. It would go into a low pressure system, push up, cool off, high pressure, push down. So just think about that as you're going through your convection current. Now let's add in that part that we already talked about with humidity. Remember, we said our warm air is almost going to hold more water. So when we have a warm surface here and that warm air is going to start to rise up, it's going to take water with it. And that's going to result in rainy weather over that area. The water is more likely to evaporate in the first place because there's not really much pressing down on it. So it's going to be able to go up easily. And then as soon as it gets up there, it's going to cool off, it's going to condense, and it's going to fall back down pretty much over the same area. And then that dry air that now has released all of its moisture is going to start to cool off even further and sink back down. If dry air is sinking down because of that high pressure, almost think of it as it pushing all the water down to the ground, and the water is held down there so tightly it can't evaporate back up. So that high pressure keeps it pushed down to the ground, and you have very clear skies in a high pressure area. So think of high pressure areas as being sunny, beautiful weather. It could be cold, but it's still nice and clear. Low pressure area is the opposite. It's going to be rainy, wet, usually fairly warm weather. So when you have those storm systems coming in, it's usually a low pressure system that's moving in. All right, so let's recap here one more time. So we have this warm, moist surface that's been warmed by the sun. And what's going to happen is those air molecules are going to start to rise and become less and less dense. And as they do that, the water vapor is going to go up with them. And this is all going to create a low pressure system because the molecules are moving upwards as they start to become less dense. And then once they get up into your upper troposphere, they're going to start to cool off because it's cooler up here. And then because of that, they're going to condense. The rain is going to fall, and the air molecules are going to cool off further until they start to become more dense. And at that point, they're going to fall because of their density. And their density is going to press down on the Earth and create that high pressure area. And this is going to be dry air that's pressing down. And then once it presses all the way to the ground, it can be warmed again, and the convection cell starts all over again. Now, I want you to focus on this bottom loop for a second. And this part right here, that flow from high pressure that air pressing down to low pressure where it goes back up. This really explains why we feel all the winds that we do here on Earth. So one phrase that you always want to remember is that wind blows from high to low. And it rhymes, so hopefully that helps. So these cold, high pressure areas pressing down are going to press over basically and create this wind, and it's going to go from that high pressure to that low pressure. And it's being caused by the cool air sinking in that high pressure zone and rising in that low pressure zone. So it's always going to go from your high pressure cold front pushing down on areas to your warm low pressure front where it's going to rise back up again. So wind always blows from high to low. And one of the things I just mentioned here is a front. So what is a front? Well, a front is where two air masses that have different temperatures, moisture levels, and densities meet. So you can basically think of it as a place where a high and a low pressure system is going to meet. And because they meet there, they're going to form this nice convection current there. And this is where you're going to get most of your storms because, as we said, as that warm air rises, it cools off and it condenses and it drops its rain. So whenever you have a boundary between these fronts, you're going to get a storm. And there's there's actually several different types of front boundaries. These are just a couple examples, but if you have a warm front moving in, you're usually going to get some light rain because your warm, moist air is coming in and replacing your cooler, drier air. If it's a cold front, you might get more of a thunderstorm. And here your cooler, drier air, because it is more dense, it's kind of sinking down below and it's pushing that warm, moist air up, up, up very, very high and creating those huge thunderstorm clouds. And that's going to create all of these storm patterns that you're familiar with. And that's going to create the huge winds that come along with them. And remember that wind is really created by those differences in pressure from high to low. Now, this also causes a couple of patterns in the winds. So there's two types of patterns. There's a cyclone pattern and an anticyclone pattern. And the difference comes down to differences in pressure once again. So a cyclone is basically caused by low pressure. And low pressure is going to make the air rise up. So as the air is rising up, it's going to do what we call converge. It's going to all come together. So I want you to notice how all these arrows are all coming together and all becoming basically the same direction, and they're starting to spiral up. And that's what forms this cyclone. It's an upward spiral, and it's low pressure, and that's why it's pushing up. High pressure is the opposite. So high pressure, you have your cold molecules and they're sinking downwards. And as they sink down, they push down. And this is going to cause winds to split apart and go in different directions as that spiral comes down and meets the earth. So part of the reason why this is going to be important is in a second we're going to talk about different types of circulation cells. And the ones that are at these low pressure boundaries are going to move up and away from the earth. And the ones that are at these high pressure boundaries are going to push down and towards the earth. And that's part of how you can remember how you're going to draw these things and see how they affect different climates. Now there's one last piece that we have to know about before we can really start understanding wind patterns, and that's the Coriolis Effect. So basically this is the idea that Earth is constantly rotating, and because it's rotating, it's going to spin everything slightly off course. So Earth is rotating west to east at 15 degrees per hour, and we make a total revolution of 360 degrees every day, and that's what gives us the length of our day. So every 24 hours we go 360 degrees. And as the Earth rotates, so this is, if you're looking down, this would be the North Pole. As the Earth is rotating, it's going to deflect objects in different directions. So you can almost imagine if you were sitting on a merry-go-round and you had your friend in the center here and you're sitting on the outside and you're trying to catch the ball. If he tries to throw the ball straight to you, it's probably not going to make it to you because the spin of that merry-go-round is going to spin it a little bit off course. So turns out that this happens all the time. So say we wanted to launch a rocket, we would have to account for the spin of the Earth. So for example, if we want to launch that rocket from the North Pole, we can't just shoot it straight at our target, because what's actually going to happen is it's going to deflect. So say we were trying to hit this spot here, we're actually going to hit out in the middle of the Atlantic Ocean here. So it's not going to be effective. So engineers have to take that into account. They have to think about this Coriolis effect. And what the Coriolis effect is really going to mean to us is it's going to spin our winds in different directions. So without the Coriolis effect, because the North Pole has such cold air pressing down, this would be our high pressure area, and the equator has a very low pressure area there because it has such warm air, so that's going to go upwards. So what we would naturally see is this circular pattern right here from high to low at the poles to the equator. But we're not going to see a nice, neat circle like that. We're going to see more of these deflected wind patterns where they're bending in a particular shape. And that is because of the Coriolis effect. And the Coriolis effect will deflect winds to the right in the northern hemisphere and to the left in the southern hemisphere. And this is also what causes water to spin in different directions in the different hemispheres. So if you flush a toilet in the southern hemisphere, it will go the opposite direction as it will up here. Now, another thing you need to know about the Coriolis effect is because of the way the Earth is spinning on its axis, there's a very strong Coriolis effect at the poles. And there's not as strong a Coriolis effect at the equator. So you're going to notice that it deflects the winds a lot more in a much more severe angle at the poles than it does at the equator. At the equator, they're going to be closer to their natural angle. So one of the things that we're going to start to see now is that when we put all of these things together and we take this Coriolis effect into account along with our convection cells that are happening because we have moisture in different areas and we have different varying temperatures in different areas, we're going to wind up seeing these belts of winds and circulation patterns around the globe. And the belts really depend on the high and low pressure zones that are there, because these winds are going to move from high to low. So these are the major high and low pressure zones on Earth, and you can see that our equator is a low pressure zone, which should make sense because that's where the warmest air is coming in. Our pole is a high pressure zone, but then we have these areas of high and low pressure in between, and you can see that they alternate. Low to high to low to high, low to high to low to high. And this is going to set up circulation patterns along with the Coriolis forces. So when we start to put all these things together, we're going to start to see these convection cells popping up that explain the way that air flows on Earth. And there's a couple different aspects of this that we're going to talk about. So we're going to talk about these prevailing winds, which are more at the surface level of the Earth down here in the troposphere. And then we're going to talk about convection cells that move up and out and cause those winds. So they're going a little bit further away from the surface. And then we're going to see we even have jet streams here too that are even a little bit further away as we get further out into space. So let's start with the prevailing winds. So your prevailing winds are all of your major surface winds, and these are going to push around the air masses in your area. They're going to affect weather patterns. They always follow the same direction. They never really stop blowing. So these are your major types of surface winds and where you can find them. Your polar easterlies are going to blow in this sort of western direction. So that's kind of confusing, is that they're easterlies because they blow from the east to the west. So you're going to see that on both poles they're blowing to the west and also towards the equator. And these are going to go from your poles to your 60-degree latitude. So either 60 degrees north or 60 degrees south. And you can see that they're blowing westward from the poles to there. So from the east to the west, that's why they're the easterlies. because they're from the east. Then you have your prevailing westerlies. So same deal. They're going to blow from the west, which is what they're named after, to the east. And they're going to go from your 30-degree latitude line up to your 60-degree north latitude line, or from your 30-degree south down to your 60-degree south. So they're going to be sort of that mid-latitude area. And then your trade winds are going to go from very close to the equator to your 30-degree north and south lines. They're actually going to blow more towards the equator, and they are going to again switch directions from your westerlies. So they're going to blow more towards the western side of things. But what's going to happen is right at the equator, you're going to have this area called the doldrums. And the doldrums are a very low pressure area. And because it's low pressure, it's going to easily absorb moisture, and it's going to take that moisture up, and it's going to condense right at the top, and it will rain right back down again. But this is what's going to set up the convection cells for the rest of the planet, basically. Is you have all this direct sunlight coming in here at the doldrums, and it's warming up that water and warming up that air and causing the air and the moisture to rise. And that's what's going to start up this convection cell, is that rising warm moist air, which is then going to cool, condense, and sink and set up all of these other cells that we're going to see. Now there is another area you should be aware of, which is called the horse latitudes. So those are right around 30 degrees north and 30 degrees south. And these are basically high pressure areas. So these are areas where the air is going to start to cool dramatically and sink back down. And what we're going to find is in the tropics, right around the equator, we have these really wet areas because of the doldrums, where it's low pressure and it's rising. And then around those horse latitudes, we're going to have very dry areas where it's high pressure and everything's pushing down. So these prevailing winds, as we said before, are more on the surface. Now we want to look at some of the larger convection cells that are coming higher up the surface that are really causing these. So the first of those, the ones close to the equator, are called the Hadley cells. And the Hadley cells occur when the air that is really hot near the equator rises and spreads out and gets further and further away from the equator. So you have this low pressure zone, it's rising here, it's getting further away, and then it's sinking again near the high pressure tropical zones at those horse latitudes, at those 30 degrees north and south. So it's cooling here, it's sinking back down, and that's creating a high pressure zone. And then as it warms up again, as it gets close to the surface, it will go back towards the equator and push back up for low pressure all over again. This is what's actually creating those doldrums at the equator. It's creating the trade winds that move in between, and it's creating that high pressure zone at those horse latitudes. And again, the whole reason this is happening is you have that really direct solar energy coming in right at the equator there. And that's going to warm the surface so much that it's going to allow those molecules to become excited and become less dense and rise. So each of these types of convection cells is going to be associated with different characteristics that you find in the area. And because this is going to create such a warm, wet area at the equator, we're going to associate tropical regions near the equator with having really high humidity, lots of high clouds, and frequent heavy rains, because that low pressure is allowing those molecules to be pushed up and condense and precipitate. Your monthly average temperatures are going to be really high, around 90 degrees Fahrenheit. You're not really going to have much of a winter season because the angle of insolation is not changing much throughout the year. Your most likely biome right around the equator here, assuming humans don't impact it in any way, is going to be your tropical rainforest, because you have so much air constantly moving and constantly moving that water around. You're also going to have stronger diurnal changes, which are day to night temperature changes, than you are going to have seasonal changes. So you won't really have much of a difference in seasons here, but it is going to be much warmer probably during the day and much cooler at night than you would see in terms of temperature differences among the seasons. Then as we move further away from the equator and we get to the other side of the Hadley cell, where everything's pushing back down, these are going to be those subtropical regions, and these are going to be areas with low humidity and few clouds and high ocean evaporation because all of that cool, dry air is pushing down. These are going to be places that have warm to hot summers, but very mild winters. And what you're going to find here is most likely either a desert or a tropical savanna, a very dry place. And it's going to be very dry because it's got that high pressure pushing all those water molecules down to the ground. These areas are going to have short wet seasons and long dry seasons. So dry seasons of at least 2 months or more because of all that high pressure. The short wet season is going to come from a little bit of fluctuation that you get as your solar radiation changes coming into the area. Normally, you're going to lose more water in these areas when it evaporates than you're going to gain back whenever it rains. It's not going to rain very much here. So overall, these areas in the subtropical regions are just going to become drier and drier. So here's one more look at that Hadley cell. So we have this solar radiation coming in here, warming this air, and that warm, moist air rises. It drops all of its precipitation right around the equator, and because it does that, it becomes very dry by the time it makes its way out here. But then it's very cool, and it starts to sink, and it causes these deserts on either side. All right, so that would be happening right here, right at your 30-degree north. You're going to get these deserts occurring. And then you're going to start to see after our Hadley cells, we have our feral cells next. So our feral cells are going to occur between 30 degrees north and 60 degrees north, or in the opposite direction, 30 degrees south, 60 degrees south. And they're going to have air moving in the opposite direction. So where your Hadley cell, air here was moving northwards from the equator and then falling at 30 degrees north, this is going to go still northwards, but it's going to go in an opposite direction. So this one was going more counterclockwise. Now you can see this one is traveling clockwise. So when it does that, it's going to bring air from the west towards the east, and it's also going to result in these different characteristics. You're going to have distinctly cold winters and moderately cool summers. You're going to have more defined seasons. Your temperature is going to change more seasonally than it does during each day. If you are near the ocean, then that's going to impact your climate a lot more here. So the ideas of specific heat are going to come into play more so. Because if you're in the ocean, you're still going to pick up some precipitation if you're nearby. And if that happens in these temperate areas, you're going to form either a broadleaf deciduous forest or a coniferous evergreen forest. But if you get inland, further away from the coast, where there's little water in the air in the first place, what you're going to find is more temperate grasslands and deserts, because there's little water in the air, and as we said, we have these high pressure areas pushing down right here, so they're going to encourage those deserts to form, especially if they're further inland. And you can see these feral cells in this picture right here. You can see them circling around and how they're moving that air around. So we haven't really discussed yet what the technical definition of a desert is. A desert basically covers up to 20% of Earth's total land area, and we can find deserts on every single continent. And when we talk about a desert, you tend to think of a hot, dry place, but really it doesn't come down to temperature. It comes down to the amount of moisture there. So deserts are any very arid place, and arid just means very, very dry. So it could be a very cold desert or it could be a very hot desert. And again, we're going to usually find these mostly in these middle latitudes, between 30 and 50 degrees north or south, because that's where this high pressure part of the Hadley cell and the feral cell are pushing down there. And the moist air from the equator has already dropped all of its water, so as it sinks, it's coming down very dry, and it's keeping, with that high pressure, it's keeping the water pressed to the ground. And whatever dry air does make it down there is going to immediately absorb whatever moisture there is. It's going to soak it up out of the ground, but the high pressure is going to keep it from evaporating so that it's not going to rain very frequently. All right, so now we've seen Hadley cells, we've seen feral cells. Now let's go even further north and look at polar cells. And polar cells are going to be in areas where you have icy, cold, dry, dense surface air from the poles that is flowing towards the equator. So you're going to have really high pressure at the poles because that air is so cold, it's pressing down, and it's going to start flowing again from high to low. Wind always flows from high to low, and it's going to push down towards the equator. And it's going to start to warm up as it gets there. And then once it warms up, it's going to start to rise up and away, and it's going to form this polar cell. So again, it's just a convection current. So in this case, we're going to see a few particular features. That sinking air is going to create a high pressure, which means that the closer you get to the poles, the less likely you are to see precipitation. It's going to create a lot of deserts, although in a lot of cases they're going to be cold deserts, so not what you would typically think of as a desert. Because of the low temperatures and the really indirect solar insolation, you're going to create some really long, severe winters and short, cool summers because you don't have a lot of radiation hitting that area in the first place. And whatever little precipitation the area does get is usually going to be frozen. So it's going to be ice or snow. It's going to be in a form that living things can't really use. Most of that precipitation is going to fall in the summer months because the high pressure will ease up a little bit then as the temperatures warm up. And this temperature is going to help to determine the type of plants that you see. So the colder it is, probably the fewer plants you're going to see. It's also going to determine the way that the soil develops in these areas. Precipitation is not going to have as much of an effect on the plants you see or the soil because there's so little of it in the first place. Now, in these areas, you're going to encounter three major biomes, either polar ice caps, tundra, or taiga. And you're going to see that as you move further away from the poles, it gets warmer and you get more biodiversity and more plants, more productivity. And the polar ice caps have almost no productivity. By the time you get down to the tundra and especially the taiga, you start to see a little bit more things being able to survive there. All right, so when we put all this together, we see that these convection cells, which are caused by these differences in high and low pressure and the moisture that goes along with that, that is going to determine the type of biome that we see in different areas. So this is very, very important. Now, I do want to just mention very quickly that these zones will shift slightly with different seasons. So this is set up a little backwards. This is actually the South Pole here, but you can see that in December, when you have more direct sunlight hitting that southern hemisphere, all of the pressure zones kind of shift a little bit more towards the south. And then in our summer, in June, they're going to be shifted a little bit more towards us. But in general, they're going to stay fairly stable, and they're going to be the reasons why we have the different biomes that we have. Now, one more idea that goes along with that is this idea of air masses. And air masses are named based on where they're formed. So if it has an M in front, it's maritime, it formed over water, it has a lot of moisture. If it has a C in front, it's continental, it formed over a dry land area, so it's not going to have a lot of moisture. Equatorial air masses are going to be extremely warm. Tropical air masses will be warm, but not quite as warm as those formed over the equator. Polar air masses would be very cold, and then your Arctic would be your extremely cold air masses. Now there's one other type of wind that's fairly important that you need to know about, and that is jet streams. So jet streams are going to be really fast flowing, narrow air currents. They're going to flow right along that tropopause, right in between the troposphere and the stratosphere. And they're always going to flow, at least for our purposes, from west to east. So you can think of them going around the globe in that direction. They're about 1,000 to 3,000 miles long all the way around, and they're 1 to 3 miles thick. They're about 3 miles off of the ground where we are sitting right now. So the jet streams are going to travel along the edges of fronts. They're going to travel right where the cold air hits the warm air, right where high pressure is hitting low pressure. And if you look at them from the side, so if we were actually on the surface here and we looked, we would see that they are right where those two fronts meet and right at the very top of the troposphere, right where it starts to turn into that stratosphere there. And they're going to just ride this front so that if we were to look at it from the side, you could see that they're going to be right where those different circulation cells meet. And they're a little bit higher and they're not pulled in by this convection. They're just going to go straight through. And that's going to drive a lot of our weather patterns. So they're going to squeeze in between these circulation cells. They're going to shift around a little bit from here to there, and they're going to shift our weather patterns with them as they move. And one of the concerns with this is something that we're seeing more and more as a result of climate change is that our jet stream is starting to basically slow down and start to what they call undulate, or basically make these little dips down further south. So it's not as much of a circle as it used to be. And the problem when it does something like this is it creates these areas of low pressure and high pressure where you get really weird weather that is not your normal pattern. So one example of this that you might remember really well is the 2014 polar vortex. And basically what happened then is that the jet stream looped down. And when it did that, it brought this low pressure, extremely cold polar system down into our area of the country, and it led to really, really cold temperatures and heavy snowfall in much of the Northeast. It also increased the drought problems in California because it brought a high pressure area up where it kept all the moisture down close to the ground so that they weren't able to replenish any of their water from that area, and it actually made that whole problem worse as well. So there is some speculation that this could be caused by melting sea ice. So as our sea ice, which has that really high albedo and reflects all that incoming radiation, starts to melt, the water that's in its place has a low albedo. It's not going to reflect as much radiation. It's going to absorb more, and that's going to cause it to heat up even faster. That's going to result in a warm Arctic. And when your Arctic is warm, and so are the areas very close by it where those feral cells are, there's going to be less of a significant difference between them. And the jet stream is going to become weaker, and it's going to be more likely to shift up or down. And when it does that, the cold air is able to seep down even further from the North Pole than normal and lead to record cold in some areas. But the warm air is also going to be able to travel up further than it would in other areas. So you might see warmer temperatures up north and colder temperatures down south than you normally should. So now I want you to really take a minute and just think about all this and how it fits together. You're going to need to be able to show all of this next time. And I want you to be thinking ahead. So the next thing we're going to talk about is how this all fits together with the water cycle and how that's going to result in a lot of the weather patterns that we see. So we're going to take all the things we talked about today and apply them to things like land and sea breezes, apply them to things like monsoons and El Nino. So that's where we're going from here. So thank you for your patience today, and come in next class with these notes and ready to go. Thanks. Good night.